In this problem, we're given a Norman window, which is a rectangle, and the rectangle has a semicircle that's on top of the rectangle. Okay, so the inner part here doesn't matter for the portion of this problem. The perimeter of the Norman window is going to be the outside semicircle plus the sum of these three sides. So if here I have the radius of the circle is r, then the length down here is going to be 2r. I have a height of the rectangle, which is h, and then the radius of the circle is, or radius of the semicircle is r. All right, what's given is that the perimeter is going to be equal to 12 feet. Now, what's the perimeter? The perimeter is going to be this side, 2r. Then I have height twice, so 2h. And then the perimeter of this semicircle. So that's 1/2 the circumference of a circle. That's supposed to be equal to 12. So said another way, I have that 2r plus 2h plus pi r is equal to 12, or that pi plus 2 times r plus 2h is equal to 12. So that's what's given. The goal is to maximize the area. So I want to maximize the area, which is area is equal to, well, the area of the rectangle is going to be 2r times h. And the area of the half circle is going to be, well, the area of a circle is pi r squared. It's half a circle, so 1/2 pi r squared. So the goal is to maximize this function given this constraint. Okay, so for this problem, we should solve for one variable in terms of the other, and then replace in here to get the a function in terms of only one variable. All right, so to do that, we'll take a look at we'll solve for h here. So if I come here, if I solve for h, I get that 2h is equal to 12 minus 2 pi over 2, pi plus 2, pardon me, times r. And so therefore h is equal to 12 minus pi plus 2 times r all over 2. And that's a bit of a mess, and that's okay. All right, now what are my constraints on the possible values of r? How small can r be? Well, r could be hypothetically as small as 0. So if r was equal to 0, then I would have a box that kind of looks like this, where it would be a very, very thin rectangle with a very, very small circle on top. That is one possible constraint on what r is. The other thing that has to happen is that the h here has to be greater than or equal to 0. And so I need to know that my r here, the h here, has to be greater than or equal to 0. And so what does that tell us about r? So if I have that 12 minus pi over 2 times r over 2, if that's greater than or equal to 0, that means that 12 is greater than or equal to pi plus 2 over r. And so my radius, the biggest it can be, will be 12 over pi plus 2. And so those are my boundaries on the biggest that r can be and the smallest that r can be. All right, so the picture that I see here is kind of silly, where I have, the r is equal to 0. This would correspond to h being 0. And so this would correspond to a semicircle. And then the box underneath is very, very thin. Okay, and so those would be the pictures that would correspond to these two endpoints. Okay, so there's my boundaries for r. We're going to need this later on in the problem. All right, now the question at hand is to maximize the area. Okay, so let me recopy what I see here. A is equal to 2RH plus 1/2 pi r squared. H I found to be equal to this. So let me substitute that in. 2 times r times 12 minus pi plus 2 times r all over 2 plus 1/2 pi r squared. Okay, so let's see. We have um uh here I have 24r divided by 2, so that's going to be 12r. Then here I have minus pi plus 2 times r squared. Then over here I have plus 1/2 pi times r squared. Okay, so I get 12r, and then I can factor out r squared. What's left will be negative pi minus 2 plus 1/2 pi, or 12r plus r squared times negative 2 minus pi over 2. And I can write, let me get a common denominator there, r squared. I've got negative 4 minus pi all over 2. And so that's the area as a function of the radius. And so I now have the area as only in terms of only one variable. Okay, now we find the derivative. A prime of r is equal to, derivative of 12r is 12. The derivative of r squared is 2r times negative 4 minus pi, all over 2. And I set the derivative equal to 0. So I get 12 plus r times negative 4 minus pi equals 0. And so bringing this over to the right-hand side, I get 12 is equal to r times 4 plus pi. And so I have one critical point at 12 over 4 plus pi. Okay, so that's my critical point. Okay, now as before, to determine the absolute maximum of a function, I need to test the critical points. I also have to test the endpoints to see what provides the biggest solution. And so I just now have to test all three of these values and see which one produces the biggest area. Okay, so three things to check. When r is equal to 0, the area function was equal to, let me write the area function at the top here. A of r was equal to 12r plus r squared times minus 4 minus pi all over 2. That was our area function. When r is equal to 0, that's easy. I get 12 times 0 plus 0 squared times this constant, and that is simply equal to 0. Okay, and that's kind of expected because the r equals 0 corresponded to this very thin line, and so I expect the boundary to be 0 in that case. Okay, the others require a little bit more thought. The other endpoint is 12 over 2 plus pi. That was the other endpoint that I figured out. Okay, and for this one, I just have to do the work and see what we get. So the area at 12 over 2 plus pi, that's equal to 12 times 12 over 2 plus pi plus 12 over 2 plus pi squared. And then I have minus and 4 plus pi over 2. All right, now that's needless to say a mess. Let's get a common denominator. So I have 144 over 2 plus pi. Then minus 144 divided by 2 is 72. Then 4 plus pi over 2 plus pi squared. And so I can write everything over 2 plus pi squared. I would have 144 times 2 plus pi minus 72 times quantity of 4 plus pi. So that gives me 288 plus 144 pi minus 288 minus 72 pi all over 2 plus pi squared. And so my maximum area, or my area in this case for this endpoint would be 72 over 2 plus pi quantity squared. Okay, so that's one possible thing. So that's not trivial, so I have to check that. And if I plug this into my calculator and just see what it is, I get that this is equal to 72 times pi divided by 2 plus pi squared. And so this works out to be something like 8.556. All right, the other endpoint, or sorry, the critical point now. The critical point was 12 over 4 plus pi. So in blue, that was the first endpoint. In red, that was the second endpoint. Now I have the critical point when I found the derivative to be equal to 0. The area at 12 over 4 plus pi, that's equal to 12 times 12 over 4 plus pi, then minus 12 over 4 plus pi squared times 4 plus pi. All right, so I get 144 over 4 plus pi. Um, I forgot the over 2, I'm sorry. So there's an over 2 here that I lost. There's an over 2. Minus 144 over 2 is 72 over 4 plus pi. So the 4 plus pi squared, I got 4 plus pi in the denominator. And so that's equal to 72 over 4 plus pi. All right, now if I plug that into my calculator, 72 divided by 4 plus pi, I get an answer of about 10.08. And so this is indeed bigger than this. Okay, so the maximum area is going to be what I just found, 72 over 4 plus pi. Okay, now the question is, what are the dimensions to maximize its area? I need to have my r to be equal to 12 over 4 plus pi. So I need the semicircle to have radius of 12 over 4 plus pi. Also, I need the height to be equal to, if I go back to much earlier in the problem, the height was equal to 12 minus 2 plus pi plus 2 times r all over 2. So just copying that 12 minus pi plus 2 times r over 2. And so I would get, let's see, so I get 6 minus pi plus 2 over 2 times the r, which was 12 over pi plus 4. So I get 6 times pi plus 4 minus 6 times pi plus 2 all over pi plus 4. And that works out to be 12 over 4 plus pi. And so the value of h turns out to be the same thing as the value of r. Okay, so what are the dimensions? The rectangle will have dimensions 24 over 4 plus pi by 12 over 4 plus pi. It's 24 because when I go back to my original picture, the length of the rectangle here is 2r. And so I need to double the radius to find the length of the rectangle. And the radius of the semicircle is going to be 12 over 4 plus pi. And so those would be the dimensions of the shape that would maximize the area if the perimeter is given to be 12.